I see that we are coming closer and closer to the end of our course, our 4 lectures in one part of solid state physics that I called electrons in periodic solids. And this lecture is given by me. My name is Andrei, and I'm working at the Department of Physics at the University of Oslo. I give a bigger course in there on solid state physics on different aspects, including electrons. In fact, before, let me show you the plan for today. So we start with repetition of intrinsic, extrinsic carriers in semiconductors. So we go also this week, probably talked a little bit about diffusion and drift. We repeat that. And then band bending as a function of carrier concentration in semiconductors. We talk about semiconductors now. We worked with general theory before. And then we talk about p-n junction. This is probably simplest component you can imagine in semiconductors. And I'm pretty sure you know about it. But let us recap that. So we actually, all the rest of these topics, these are related to p-n junction and physics of p-n junction. I hope it is going to be relatively familiar for you, this topic, p-n junctions. But we will do it very carefully and gradually progressing. But before we start with this plan, I want us to warm up. And what we are going to warm up with is this quiz. So let's see what we see here in quiz for semiconductors. First question here. What are basic assumptions for effective mass method? Nice that more people came. Don't be shy. Just go in and take your seats. I feel like I'm cabin attendants in an airplane, so I need more customers to come. So the more coming, the better airline is going. So very good. Let us see. What I propose now is that we warm up a little bit, we repeat or try to remember with the help of this quiz. And we talked actually quite a lot about effective mass approach last time, because this is a basis for semiconductor physics. In fact, that would be different opinions, but in my opinion, whole semiconductor physics is based on effective mass approximation. Then my question is, what is actually effective mass method? What are the foundations for that? What is it about? What are assumptions? Can you please try to recap it, try to remember? You can discuss, build groups. It's a perfect group of 3, perfect group of 2 and 2. Try to discuss and try to remember what effective mass method is about. This is a question to try to remember. And why we need it. Why we started with that. And then, while you are discussing in small group and considering, I'm going to draw some figures here. So in this, the rationale here, we always want to know energy of interaction of electrons. Then we can calculate other properties. And energy, in the simplest case, when electrons are free, then energy is equal to this. I remember it. I wrote it so many times, but you may think it's a complicated equation. It's not. It's a parabolic equation here, and this is how energy is changing for free electrons in a material, in a periodic material. And that is the first, let's say we have had that one-dimensional crystal. So it looks like this. And then why do we need, if this is so good, if you can calculate energy of free electrons, why do we need any other more complicated theory? What are assumptions? What is the requirement? What is the driving force for that? Can you please talk a little bit in between each other? Okay, so what was this about and why we need it? Let me start answering this question. We need it because we don't have only free electrons in our crystal. You remember this diagram that I used to draw. So if say I would have a two-dimensional lattice, and this is K space, for instance this is Kx, and this is Ky, two-dimensional lattice. If my electron has a small energy, then it is really free. It doesn't interact with the crystal. But if electron has high energy or high K, when it comes to the vicinity, close to the Brillouin zone H, then interaction stops. We talked so much about that. So exactly around these points for one-dimensional lattice, we have interaction between electrons and lattice. So exactly in these regions, this solution is no longer good. And we need some other theory to explain that. But the perfect would be to solve a Schrödinger equation having kinetic energy, let's say kinetic energy, energy plus potential energy, then we have some, let's say this is a Hamiltonian, including these energies, and then we find this. And this is how we actually found that. We neglected potential energy and we came to this solution. And then now if we have to include potential energy, we have to know the form, we have to know how it works. We have to know if it is, say, imagine these are atoms, and there are so many. If there are only two atoms, and if there are point charges, we can think that it's purely Coulombic, correct? If there are only point charges. But for instance, this charge is going to be affected by this, and that. So it's really not pure Coulombic interaction of 2 point charges. The problem is that we don't know potential energy. We don't know the form. If it is 1 over r, if it is 1 over this, or maybe this, or maybe, I don't know, this, who knows? We don't know that. And because of that, we need some other approach. Not this, let's say, straight approach, but approach that can still resolve what is the form of interaction here. And the way we do it, we qualitatively first, if you remember that, we said that, okay, there is, in these points here, we have diffraction happening. We talked so much about that. So then we have qualitatively shown that there will be this type of shape of the dispersion relation. And going to be like that here. So there is a band gap here. And what we said, and what is really effectiveness approach is that we don't know this function. But in the vicinity of extrema points, for instance here and here, we can expand the function as a Taylor expansion. So the function is expanded like this. Just magnitude of the function in this point minus first derivative of the function, and then plus second derivative of the function, and then minus further on and plus. It's a series. So then the answer to this quiz question, what are the assumptions? Basically the assumption is that we can expand the function in the vicinity of these critical points as a Taylor series. And then we neglect, this is going to be 0 because first derivative is 0, and this we put to 0 because we can start at any point of energy and put it to start our scale from there. It's just start of the scale. Then we only left with this one. And then we started to see, maybe I could just write, instead of this, I could just write energy here, because we are talking about energy explicitly. Then we started to see if I have this, of course I have to multiply it by k squared, and this is by k. Then we started to see if this equation is like this, and this equation is like that, they are so similar. If you just call some parameter effective mass, so we can write that this is equal to exactly similar form of equation. If this parameter effective mass is written like that. Yeah, so that is the theory. And then let me ask the next question, because that was probably too abstract. But the next question is very straight. Can you please read the next question here? The first one, the first sentence. What are the electrons in materials? It's relatively obvious, correct? We believe that electrons are actually rotating around atoms, and when we connect atoms, they got free, got to electron gas. Okay, probably obvious. It is also accepted that electrons are negatively charged. But what are the holes? This is my question. We talked also about that quite a lot. And I was saying, wow, now we are going to have a discovery. What are the holes? Can you please discuss this question? What are the holes? And then I continue, giving you a hint. Conventionally, the holes are considered to be mobile positive charge carriers. Then I'm asking, explain what is the nature of these positive charge carriers, where they are coming from. Indeed, in materials, there should be no positive charges. It's not possible, only electrons. Some kind of interesting question. So can you please spend time discussing this question this topic in the groups, please. So you don't have a group, but you can talk to me. I can build a group with you. Yeah, if you want. I grab a coffee. Yeah. Yeah. So have you read the question?
Yes.
Mm-hmm.
I think vacancy that electron left. The vacancy site that electron left is more.
What is the vacancy site? Vacancy is
Because the velocity of electron as holes are different. So I think the vacant site that electron left
yeah, I know exactly what you want to say. This is a sort of primitive explanation that was taught in many courses. But I have to tell you now that this explanation is not correct. It's actually like if you compare, I don't know, you compare what you see, you go to, I don't know, how should I say that, what comparison I should give you. I don't know, you go to George Island and see the waves coming on the cliffs. And then you have a cartoon, someone did this painting, and it can be totally different impression. Okay. So the reality is different. I think we have to talk about this more, guys, because I really want you to understand it. Maybe this is the only thing that you will never hear from anybody else, because nobody else cares about that. There is a model, and I think this is what Kuocw want to say. Very often, the only explanation what happened that is given is in these terms. This is conduction band age, this is valence band age. Let's say at zero temperature we have all electrons occupying valence band. And here we have many empty orbitals. And then temperature is increased, and we have an electron from here coming up to here. And then what probably is written in some books, that here is left a hole. Correct? You know, this is so big abstraction. Because there is, it's really, this is, I don't know if you ever thought about this. This is the energy scale. There is no really, I mean, situation in real space as electron go from one place where it is electron to another place, leaving a hole, as you called it, vacancy. It's not like that. Electrons, of course, they are moving, but they're just changing energy. So this is not it's not a vacancy. It's an empty orbital. But what I tried to tell you last time, and which is really truth, that there are only one type of thinkable moving particles in the crystal. These are electrons. But electrons may have different properties if they are located with this energy or with that energy. I don't know if you remember that. Then we investigated this plot, and we made several derivations of this curve. And we discovered that second derivative of this curve, that is here, that actually determines the effective mass. When we make a derivation, if you remember, maybe you should make an effort and think about this now, because that is probably the moment is not going to repeat it again. When you do the second derivation of this function, then for these electrons, you got a positive value. And for these electrons, you got a negative value of the second derivative. Because here, curvature is like this, and here curvature is like that. So it's like this. And then you got a parameter that, okay, you can put it like 1 over this. Because we need to have it in there. So you have a parameter that can be either positive or negative. And this parameter is not a charge. This parameter is a mass. So, because electrons cannot change charge, it's like you ask, it's like, you also have a lot of gods, so used to have. People cannot be gods, we cannot change to gods. You have to be born as a god, correct? I don't know, maybe you have a different kind of religion here, but usually you have to be a god to be it. You cannot change. The same with electrons, they cannot change. They cannot change to positive charge if they make this transition. They just change the energy. So in this case, electron has had this energy, it went up to there, it has this energy. But it's the same electron. The only what changed is that there is an empty place here, so that these other electrons can start moving to this place. This is the only that can happen. But these electrons, they are already here. And these electrons are exactly electrons having located here, having negative effective mass. How can I bring this back? Yes, thank you very much. This is really very fundamental situation. Holes. My father, he was also a semiconductor physicist. And one time, he told me also this, that I couldn't understand it one day. And holes. Actually, my explanation was exactly like Frank Jung said. This one, that there is a process when electron is moving up and leaving an empty vacancy. This is a primitive cartoon. It has nothing to do with reality. I mean with reality of creating a positive charge. Because this doesn't create a positive charge. It also electron here. It's the same thing. It just changed the energy. Here it has this energy, here it has that energy. Just because of thermal excitation or because of light coming, correct? We can excite it just by light, correct? And then we have this electron here, an empty orbital on the valence band. But the electron is electron. But what is important that when electron is here, then it has a low k vector. When electron is there, they have basically here. So they initially, there are two types of electrons in the material. That part of those interact with the crystal, part of the electrons does not. And then for those that are not interacting, okay, no problem, we call them electrons. But for those that are interacting with the crystal because of their negative effective mass, what does mean negative effective mass? Yes, that if you for instance have current, which is equal to field, correct, times I don't know, resistance or something, conductivity, correct, something like this. Oh, wait, yeah. So the current, what is Ohm law? So now I'm getting puzzled. So resistivity, so anyhow, this is equal to Z, correct? And then current is equal to this over Z, and then this is change of the potential. Anyhow, when we apply potential, when we apply field, then these holes, so if you have a, okay, let me put it geometrically, if you have a field like this, and I have positive charge, then it will, actually I don't have positive charges, I have negative charge and negative charge. But this one has a positive effect in mass, and this has negative effect in mass. Then this one will move that direction. But this one will move along with the field. It will move, this particle will move exactly like it would have positive charge and positive effect in mass. And then we say, okay, to don't make a trouble, we call these holes, even these holes are electrons. This is what I said, this is what one time my father said to me, that holes are also electrons. I was so puzzled. Why holes are electrons? Yeah, because there are nothing than electrons. As I said, there is nothing. It's like not possible, only electrons. This is why we solve all problems for electrons. And then we find that two types of electrons may have two different properties. One have a property like that, say normal electrons, and others has a property like this, abnormal electrons. And we call these abnormal electrons holes, to make it short. And then when we know this, I don't know if you agree with me now, then of course we can use this interpretation with no problem. Then this interpretation is good, as long as we understand that this is not a vacancy, this is just an empty orbital that is available now for these electrons to move. And these electrons are holes. Actually, it's not empty orbital. These points that occupy orbitals are already holes. We don't need to make an excitation to make these objects to holes. They are already holes. Do you understand me? You think so? Yeah. Okay, discuss in the groups what I said, if you agree with this or not. Discuss these ideas, please. Because it's really important, and it may not be possible you hear it from somebody else. Yeah, my coffee is here. So what do you think now? So your interpretation was correct, in fact, but it is a simplification. It's like a step which you can use if you don't understand, or you can use when you already understood the mechanism, the real mechanism. You just use it for easy interpretation, like this. Okay, very good. Let us take some specific questions about semiconductors and then continue warming up. Intrinsic charge carrier generation in semiconductor, what is that? We already have it actually on the whiteboard. Correct? So it is exactly this situation. When we have a carrier that was here, but when the carrier was there, it was like a correct, but when this electron was inside the valence band, then the material was not conducting at all. Why it is not conducting? Why it is not conducting? Because there are no empty orbitals here. Electrons cannot move. They can only change energy to another empty orbital. And this distance was so big, there was no yet generation. But then, when temperature goes up significantly, we have this intrinsic generation up to here. Then we have electron there, and we have empty orbital here. Not a hole, actually. Empty orbital. But you can interpret it as a whole. But of course, you have to think that this is not really empty space, empty real space. It's just the energy state that got available. This is intrinsic generation. Okay, let's probably check one more question. I don't remember what is the next one. Yeah. Yeah, this we discussed many times already, maybe 2 times. What, and I know you're good in that, what is the temperature dependence of electrical conductivity? So, prism of conductivity, what would be, you think, is the dependence here? Yeah. So if the material is intrinsic, then we have only that process, and this process is proportional to that exponent, correct? KBT, correct? So we have basically multiplication of effective density of states here to the effective density of states here, and then this factor. So then it will be just a line, correct? And then if you have an extrinsic situation, then it will be slightly different, as you know. Then you have some faster generation first, some situation like that, and then we will come to the same slope, basically. Yeah? Something like this. Or maybe should be like this. Yeah. Correct? Correct?
Yes.
Yeah, good. Okay, let's check what I wanted to emphasize in the lecture, because we have some more questions. We can take it later. For instance, about hydrogen atom and things like that. Okay. So this was our basically we already started to repeat what are the intrinsic, extrinsic carriers, and what they have an impact, what kind of impact they have on electrical properties. So if you have in particular silicon, and we put extra electron, an atom with an extra electron inside, this is hydrogen-like atom, correct? And this is also almost hydrogen-like, mirror-like atom when we have absence of one electron. Maybe also refer to this, that we have, you called it as a vacancy, but this is not really, you cannot localize it. So immediately when you put this thing inside, this bond can get free. so to say, they can get exchanged with other bonds. How can we change the carrier concentration? Because you see, like it is here. So changing carrier concentration, changing electrical properties, and it's what we want to do. And as we discussed, also started to discuss last time, there could be diffusion or drift. Basically, there are two processes to change electrical concentration. Diffusion, when you have high concentration, low concentration, like this. If you have low concentration of electrons and high concentration of electrons, they will start diffuse. And of course, it will be proportional to the gradient for electrons and for holes. The same thing. And then when we sum up this, we may have electron current consisting of two components, diffusion and drift. Drift is just charge times electric field. And of course, concentration. Yeah, let me probably go to this because I really want to come to p-n junction very, very fast. So when we change the concentration of electrons, that also results into band bending. Why? Because we have to, so if the material is more intrinsic, and if the material is more doped, like it is here, so if it is happening as the same material, so the Fermi level is at equilibrium is at the same position. So then what happens is that the band is banded to feed the Fermi level actually between these two parts, heavy doped part and lightly doped part, correct? And that situation can happen either by physical doping of the material, correct, or by, for instance, illumination. So if you have N-type material from the beginning, and if you illuminate it from that side, here we will create electron hole pairs just by illumination. So there will be so many holes that they will be almost in equal concentration with electrons. So then we will get this type of band bending. And then I have some equations on the next slide describing how big band bending is going to be. So for instance, if you have exactly the material on the previous slide, then the band bending difference in the wall, I mean, basically what is that? Say it's difference between this level and that level here. So that difference will be just proportional to the carrier concentration ratio, which is also very, very obvious. But it's good to remember that when we go to the p-n junction. And as I said, that can be reached by physical doping or by illumination, by carrier injection. Many of you work with LEDs, so this is what is happening there all the time. Now I want to talk specifically about p-n junction. Even I know that you know it. That you had the construction engineering studies.
But
you
know about it.
You know about this. You too. Okay, let's see. Because I have a very basic explanation here, and I will try to ask questions, and you give me answers. p-n junction. Let's say we don't know how it works, but there are steps, and this is how it is explained in the books. So we have what is this schematically shown here? This is p-type material, correct?
Yes.
So this is a conduction band, valence band, and this is a Fermi level, closer to the valence band edge. And what do I show here? So these cycles, what is this? These are, I don't know, say, let me make a comparison here. Now I'm getting confused because maybe these figures are switched actually. So this okay. What I have on the next slide? I don't know how it happened. Yeah. So basically, what I wanted to say is that there is one mistake in this. So these pluses, these are holes, mobile holes, and these cycles should be with positive charge too. These are atoms. So maybe I could draw it here. I can use this whiteboard here. So what I want to say is we have materials with maybe there are too many pluses and minuses there. Maybe what I wanted to show both electron and holes in these samples, but basically better drawing would be this. If this is p-type, then we have mobile holes here, just pluses. And this is n-type. We have mobile electrons. Maybe that would be a more simple drawing, correct? But why do I have this drawing? I think what I want to emphasize that even on this side, I will still have some portion of electrons and some portion of holes on that side, but maybe not so good drawing. But anyhow, if we refer to that, and then question is what band structures are. Okay, everything is fine. But when we put it together, before we put it together, we have we have positive mobile charge. We have also a little bit of positive mobile charge on that side. Then we have a lot of acceptor concentration on this side, and then a little bit of electrons, very little of donors. So this part is electrically neutral. That's normal, okay? And then the same here for electrons. So we have more donors, less acceptors. This is n-type, but still electrically neutral. Then, as it is done in textbooks, we put these things together. What is happening? What should happen? If and this is what I'm going to ask you now, a question that at time zero we put these two pieces together. What is happening? What should happen? We have high concentration of mobile particles, holes on that side, and we have little of this. What should happen? Diffusion, correct? Immediately diffusion should stop. And basically, we know that diffusion should continue until the concentration is equal, potentially. And so these things, they cannot diffuse because they stay in the lattice. So these are donors, these are not mobile charges, correct? There are two types of charges. There are mobile charges and stationary charges. Do you see the difference between mobile charges and stationary charges? Okay. Then for electrons from n-type, also diffusion should start. Then my question is now, if you have high concentration of holes here and low concentration of holes here, and high concentration of electrons and low concentration of electrons, so there will be diffusion in both directions of these particles. The question, until what moment this diffusion will continue? Will it continue forever, or there is some parameter that stops this diffusion? This is a question. Have you thought about that? Once again, there is a concentration gradient. More here, less there. So particles just start to diffuse. But will they diffuse forever, or will they stop diffusing? This is the question. And that is a basic idea of how p-n junction established. Please, did you understand the question? Good. Can you please think or discuss in groups? Yeah. As usual, we discuss together. We spend so much time together, so we get used to that. Yeah. So, did you get the question? So the question is, we have more particles on that side and less particles, like balls. They start to diffuse. The question is, will this diffusion continue forever, or there is some condition that is going to stop it? Maybe already in the questions that I state, you can guess that there is some moment when diffusion should stop. What is this condition?
미세적으로 마이크로 when drift current same as equals with diffusion current, I think diffusion
they have different opposite.
And what is the reason for the drift current?
electric field.
And what is the reason for electric field?
Electric field is difference.
Very good answer. Yeah.
Because electric field,
Because of uncompensated charge.
Yes.
And where from this uncompensated charge comes?
The dopant.
Correct. Very good. Very good. You know that. Very good. Because this is really for when you talk, it means you know that. But very good. You're absolutely correct. So once again, there is a gradient here. If the particles would be just on their own, they will just continue diffusing, no problem. But as you said, every moment when this hole goes out of there, it leaves uncompensated acceptor behind. Absolutely correct. So this will not go on forever, because this is exactly, so but from this region, so here we have a lot of holes. There have been a lot of holes here too, but now all these holes diffused away, and they left behind uncompensated charge of ions, of ionized ions, in this case acceptors, and in this case oppositely donors. So exactly, very good. The reason for electric field is uncompensated charge. That's Gauss theorem. Is immediately when we have uncompensated charge, we have field and we have potential. So this is great. Of course, unfortunately, not for the first time. Like with this. With this, I was the first time to tell you that electrons are, sorry, holes are electrons. but this, of course, you know, you knew. But still, it is a fantastic situation. We have carriers start diffusing from here and there, and they get out of the region, but not only that, but they have uncompensated charge. I mean, they live in uncompensated charge behind themselves. And you're right, this process will equilibrate. When the drift current created by this field is equal to the diffusion current, then everything is going to stop. And that I used to show to my students, because you are very knowledgeable. I have a diagram here that I show to my students always. You will not recognize it, but students in Europe recognize it. Of course, we don't study religion now in schools. But this is a picture from Bible. It describes one of the miracles that one of the prophets in Bible made. So I don't know, you don't know Bible very well, and I'm not teaching theology here, but there is a story that one upon a time, Jews been exiled to Egypt, and they wanted, I don't know how much geography you know, but Egypt is in Africa, and Israel is in Asia. There is a Red Sea that is in between. And Jews want to go back to Israel. And on their way back, they have to cross the sea. And they could not, because it's water. And then there was a prophet there who led them through the sea. And this is what I'm saying, that of course there is a lot of diffusion of water. Water should just, it's a miracle. But what makes them able to go? Because they have magic. So you see this stick, it's a magic. It's like electric field. You know, there is diffusion current going around. And this is magic. It's really magic. I found this comparison so great. Because I go back. Because this is really magic. So carriers should diffuse. For this also, for this story from Bible. Of course, water should just spoil them. But he has magic to stop water. Exactly like this field has a magic, actually not magic, but real nature of that, is that it stops carriers to diffuse. I think this comparison, at least in Europe, it works very well. Because even it's from a magical field of Bible, or I don't know, who knows, the different opinions. Some people believe in that. Do you understand my comparison here?
Yes.
Yeah. So what I want to say by this comparison, that p-n junction is really magical component, and this is true. I mean, of course, it's practical component, but imagine how much progress has happened just because of this little thing, because of little p-n junction. Everything we have in here, it's crazy many p-n junctions inside, except other components, of course. Yes, this is my explanation for, or at least comparison for the dial. It's magic, but we can, actually we are so clever that we can describe this magic in equations. And this is how it is done. So we can really describe these profiles very, very precisely and very carefully in mathematical terms. So what is being done? It's introduced electron concentration on electron side, electron concentration on p side, and so on and so forth. And actually you can really calculate these profiles depending on the properties of the material and depending on the magnitude of the gradient. No. Yes. This is how it is, and this is how the field is distributed. And then, of course, there are never these sharp kind of forms, but it's exaggeration here. What is really done, and why it is so easy to do in this approximation? If we have this sharp, I think it's called sharp p-n junction or something like this, or I forgot this name, but basically what we have to assume that we know the number of charges on that side and number of charges on this side. Immediately, if we assume that we know, we can calculate the field and we can calculate the band bending and the potential. And I do this calculation just on the next, it's called depletion region. Yeah, I do it just on the next slide. If I assume I know, if my whole concentration I believe is equal to acceptor concentration, I have this, that, and then I use these charges on the both sides, and then I can calculate what is going to be this is just a calculation of the Fermi level position. And then when I feed these two together, so I'm going to get this part disappearing, and then it will be just ratio between product between acceptor and donor concentration over intrinsic concentration. So this is how it is. And so you see, we are magicians here. We have a magical component and we could describe how it works. Even this simple component, it's still magic, but of course, imagine you have very, very complicated type of LEDs that you work with. It's really great. But just a little bit of more of these common things that, of course, you can have more dopant on one side than one of the part of carriers can be neglected. If you have non-symmetric junctions, then it will depend only on the lower doped part concentration. So only N-type situation that determines really this. Why? Because the field is always penetrating into lower doped material. Yeah, I don't know. Maybe I can just. It's exactly this situation. So the field is penetrating lower doped material, and this is a kind of diagram that summarizes the situation when all currents are equilibrated, perfect p-n junction in equilibrium. Can I ask you a question that you also know? It's nice when I ask questions that you know. These questions get more and more difficult. What is going to happen if I apply forward bias to this? Of course you know. Then the depletion region will shrink, and then the barrier will be lowered. So we open the diode for the current. I actually talked a little bit about that yesterday when I talked about power electronics, if you remember that. When I talked about gallium oxide comparing to silicon, that if I have a device, if I have a diode, say this is a diode, I don't know, gallium oxide diode, and this one is silicon diode. Why this is so much bigger? So I want to block a voltage, and these two materials. Imagine I want to block one kilovolt voltage. Why I have to build bigger device here? Yeah, because this material doesn't tolerate so much field per centimeter of length. So I have to say if this is, so imagine this is distance and this scale is field. So I cannot put all my field in this region, then it will break. So I have to put the same amount of field but very gently up to some here. You understand what this field is? It's exactly this this one. So if I put too much field in too much volume of the material will not tolerate that. It's like exactly no materials, but this parameter is low in silicon and fortunately high in some other materials. So it means that if I want to make a silicon component to block this, I have to put more material because of low breakdown field. Here breakdown field is high, so I can make it smaller for the same doping concentration. And why then it is so good? Because as you see, when they block voltage, they block totally identical. But then at some point of time, I want to put this component in a socket, and I want to open them. I want to let current to go. But then this big one will act as a big resistor, and this small one will act as a smaller resistor. And you know that the power is equal to, proportional to, so voltage kind of like this, correct? So the more resistance, the more loss of power. Do you understand this point? And that is very much related to how material tolerate the voltage, and how, and this is the way to calculate. Maybe I can just because you know all this. So when we put more reverse bias, we increase the field, and then when we put less reverse bias, then we, I mean not less, but when we put it in forward bias, then we decrease the field. So exactly, and decrease the potential. So I think I'm satisfied. I feel that you know this topic really good. This type of components. So what I'm thinking, I want to stop this material here and probably go again to the quiz questions. Before, I also want to summarize a little bit. I want to devote some 5 minutes to summarize all lectures all together. But before I do that, let us try to remember and try to comment on these questions. So hydrogen model, hydrogen atom. Electron rotating around hydrogen, I mean in hydrogen, around proton. What energy does it have? This is proton, this is electron, and this is hydrogen atom. There is a model that we talked a little bit about. So when we calculate the energy of this electron, then the energy is going to be 13.6 eV. Quite big, correct? Then, if we think about phosphorus and silicon, it's almost like this. We have phosphorus donating one electron. I mean, not yet donating, but it connects to silicon in all with all 4 bonds, and then there is one extra electron. It's hydrogen-like, correct? It resembles hydrogen. And then instead of this big energy, if you calculate, you got this small energy. What makes the difference? That's the question to remember and to discuss. Please. It's free to talk. Everybody can talk between each other, can think, can read the question a couple of times. I can repeat it as well if you want. But maybe you can think and discuss. There is hydrogen atom. It brings you so much energy for electrons rotating around. There is phosphorus atom inside silicon. The same electron rotating around positive charge. But the binding energy for this one is very small. What makes the difference? They are so similar. Yes, please have a conversation together. Okay. Can I talk with you guys in your group? What makes the difference, you think? But once again, do you understand the question? There is a system, positive charge, negative charge rotating around. So the energy of this rotating positive charge is 13.6 eV. Then we have a very similar system, phosphorus and silicon. All electrons are connected to silicon except the one. So it also rotates. It also binded to phosphorus, but it has much lower energy. Why? Yeah. So you see, this is phosphorus. This is exactly that electron, and it actually exactly belongs into here, like hydrogen. It's very similar system. Here we have relatively big energy of this, and here we have relatively small energy. So the model is very similar, but there are some parameters that has to be adjusted, and this is the question. Anybody wants to explain? Please, don't be shy. We talked about that last time, I think. And if I don't, of course, I don't remember this equation, even if it's not so complicated. But what I know that when I have energy of this, of hydrogen electron, maybe there is some charge, I don't remember in what power, let's say proportional. And then there is mass and there is permittivity. There are more things. I would guess this is in some power 4, or I don't remember, or maybe 2. Anyhow, here is gravitational mass. This hydrogen molecule, atom is kind of considered to be in vacuum. This is also vacuum related. So if you change this to effective mass, and that is changed to a product between permittivity and dielectric constant, then this value is going to change. This is the only reason. Otherwise, the systems are very identical. In fact, I can tell you that I used to give a problem in this course to calculate so-called. You asked me to give a hint. Now I can give you a hint about problems. To calculate. So for hydrogen, this trajectory. This is hydrogen and this is an electron. This trajectory is called Bohr orbit. And what I often do is ask to calculate Bohr orbit for phosphorus. For instance, for phosphorus dopant in silicon. Also, maybe you can remember that, maybe not. But for instance, this orbit, how big is this radius? Can you guess? We haven't calculated this, but you can think it is very small, correct? Hydrogen molecule is atom should be small. I don't either remember this now by heart, but very small, maybe a couple of angstroms. But this one, how do you think, how big is it going to be this one? This is really interesting. So if this was hydrogen and this is phosphorus connected to silicon in the lattice, all electrons are connected, but there is one electron that is not connected to the bonding. And then this question is to calculate what is going to be the radius of this electron rotating around phosphorus. And I can tell you that this radius is much bigger than the boron radius, but still not kind of kilometers. It's still a couple of tens of angstroms. Yeah, so very good exercise, really. Okay, so instead of continuing these questions, I would recommend you to look into these questions. I have formulated them not by chance. As I said, these questions, they basically give you a frame of possible, questions you can be asked if there will be exam or something like this. Yeah. Let me just finish this the whole thing. Oh, sorry. Why? Yeah. By repeating what we've been doing here. We looked into one specific topic of solid state physics, and these are electrons in periodic solids. In bigger courses is that really when you start the condensed matter physics, if you simplify it to a good extent, but still not washing out the meaning, still it is about waves in periodic lattices. Because electrons are waves, and for instance vibrations are also waves. Vibrations, understanding how elastic waves, vibrations penetrate, gives us thermal properties. Understanding how electron waves penetrate in crystals gives us electronic properties. So, and actually there is a fantastic similarity here. What we calculate density of states here, calculate density of states there. We use some appropriate distribution function here and also here. So we see what energy states can be reached. And then in particular for electrons, which is actually slightly different comparing to here, we can have two models. One model, wave penetrate in this periodic lattice, and it does not interact with it. Why? How can it be possible? Very easy actually. It's even normal. It's normal for waves. I have it here. It's actually very normal for waves to not necessarily interact. They just go like this. And why they do it? Yeah, because mathematically speaking, so the k vector is, as long as it does not come to the boundary of Brillouin zone, it is not in diffraction conditions. So as long as k vector is small, we have free electron situation. And this is also seen here. When k vector, k number is small, we are just here. No interaction. Very good. Situation is great. And we have a very good equation for energy. And this equation, I also request my students always, make like this and being able to write it, because this is so nice. Yeah, this is great equation. This is this parabolic thing. specifically very good for low K numbers. Then, if we come to a situation when K is big, K comes to this range, to the boundary of the Brillouin zone, then we need next step. And the ultimate next step is if we know what is the potential energy of interaction between electron and the lattice. But we don't know it. And one hint, one way going around it is to use effective mass. By saying, okay, we don't know the function, but we expand it in Taylor series exactly here. Because here we know this region, we don't need to care. These are free electrons. It's only close to these areas, to this. When K is big, we need some improvement. And it is exactly here we can expand, because this is a critical point. It's a mean point. We can expand the function in Taylor series, and instead of this, we got a very, very similar equation actually. Almost the same, but with very significant difference. That here we have no interaction, just normal mass. Interaction with the lattice, we have effective mass. So all interaction with the lattice goes into effective mass. Yeah. After that, we know all energy for this system, and then we can do applications as we did with semiconductors. So maybe I stop here. Thank you very much for attending the course. Thank you. Bye bye.